We're starting chapter 5 now. This is the chapter on probability, and it so far what we've covered are the first four chapters. The chapter 1, again, I'm just sort of reminding you where we've been and where we're going. Chapter 1 was about data collection. It's about what researchers and statisticians and data scientists do. You ask questions and you have to obtain the data to help answer the question. And then you've got to start doing descriptive statistics of the data you collected. So you want to keep track of the data to help answer the research question, but that's always at the forefront. What questions are we trying to answer? So chapter 2 was about organizing, summarizing, presenting the data. Chapters 3 and 4 had more a look at summarizing numerically the data, and then, how to think about bivariate data. A lot of times data has a split between the explanatory variables in the data set and the response variables. That was chapter 4. And we did a lot of work in both quantitative and qualitative data sets. And so now we're on probability and probability distributions. Distributions is chapter 6. Probability is what we see in chapter 5. As people join, just want to thank you again for joining today. And what's good about joining is then you can say something in the chat, put your hand up, and then we can answer questions in real time as we go forward. So, first, the definition. Probability is the measure of a likelihood that something occurs. And this is sort of obvious. People have a general sense of probability, but let's start with that definition. It's the measure of the likelihood. And this is really important because statisticians always talk in likelihoods. They talk in probabilities. It's sort of the currency of what statisticians use. It's the language they use. Okay. So 5.1, chapter 5.1 is about the rules of probability. Okay, we're going to talk about the law of large numbers, the empirical, classical, and subjective method at understanding probability, the likelihood. So part of this is randomness, and we have to understand a lot of things are random. So random means unpredictable. The outcome is unpredictable. A simulation is a way to sort of get at randomness. We can simulate randomness, and that could be physical, like picking a card out of a card deck or rolling a cubed six-sided die, or we can do it virtually. We can actually simulate these uh, tactile events in software, and this is actually a modern thing that's happened in statistics. When we finish chapter 5 and the section on probability, we'll have a better sense of how statistics and analyses has changed because of software doing things virtually. So in both cases, both tactile, virtual, we're going to simulate and we're going to measure the outcome. Okay, measure the outcome. Again, that's the definition of probability. Measure of the likelihood of the outcome that something occurs. So let's just take an example. We flip a coin 100 times and we compute the proportion of heads observed each time we flip a coin. So we're just measuring the head proportion, the percentage of heads as we keep flipping a coin again and again and again. Now, these are two simulations of flipping a coin. And you can see on the figure A here, and hopefully you see my cursor. In figure A here, what we're demonstrating is the whole sequence of 100 coin flips. The first one, though, is it flips tails. That means that after one flip, the proportion of heads is 0. The second one's a head, so we get 50-50. Third one is another. We toss it to another head, and then we get that's 2/3. So we keep flipping coins 100 times, and this is our simulation. And you can see it gets close to zero point 0.5. Okay, it gets close to zero point 0.5, not exactly, but close to zero point 0.5. And so that is our probability now. Okay, good. Then we go to the other simulation. It starts off with two heads, head, then we get a tail, then we get a bunch of other flips. And by the end of 100 flips, we get to 50% heads, which is what we'd expect with a fair coin. Okay, we expect a fair coin to be 50-50 as long as we do it enough trials. But we can see in A after one, it's 0% heads. And we can see in B here, after two, it's still 100% heads. But again, do it enough times and you expect the 50-50 proportion is the expectation. And so this is what we call the random process, okay? It's the scenarios and the outcome of any particular trial may not be known. It may turn out that we do it 100 times and the percentage of heads is 50, or it might be 55 or 45 or 46%. Okay. It's unknown, but as we get further and further, and this is the law of large numbers, as we get further and further, the relative frequency or the proportion is going to get to a specific value as the trial number of trials increases. Okay. So probability, again, is the measure of the likelihood of a random phenomenon, okay? And it deals with experiments, trials. We try something, and then we measure outcomes. So it's a likelihood of a certain outcome, and the long-term relative frequency, the long-term proportion is what we call the probability of that outcome. So these are just definitional. They should be relatively intuitive to everyone. But here is the definition of the law of large numbers. As the number of repetitions of a probability experiment increases, the proportion with which a certain outcome is observed gets closer to the probability of the outcome. So there's proportion, which comes from the trials, and then there's the probability of the outcome, which we expect to see as we go forward. Again, the figure here is showing that as time increases, the number of trials increases in our little experiment, um, it gets towards the probability, the true probability of the outcome. And the true probability of getting heads on a fair coin toss is 50%. You can see the proportion heading to 0.5 here. Now, this is the law of large numbers. It's not the law of averages. So just keep that in mind. People get confused. It's the law of increasing the the observed number of trials getting towards the true probability. Okay, so the experiment is any process that you do that's going to be repeated. Now, definition. This is a definition that's important. We'll use it all through the probability section. Sample space, capital S, is the collection of all possible outcomes. An event is a collection of outcomes of a probability experiment that we're interested in. So, the probability consists of one outcome or more than one outcome. And, so we have simple events that are E sub I, but the events in general that we care about is capital E. So we'll see capital S, capital E, and in some of the formulas, we'll see small e sub I using the I as the subscript for all the different trials that might be run during an experiment. These definitions hopefully will become more clear as we see more examples. So here we go. Example of rolling one die, a single fair die. What are the outcomes? Well, we can roll a 1, 2, 3, 4, 5, or a 6. Okay. So we get each of these small e events of rolling one of those numbers. Those are the outcomes. And the sample space, by definition, is 1 or 2 or 3 or 4 or 5 or 6. The set of those 6 numbers is the sample space for rolling a die. And we'll see other classic things. The sample space of flipping a fair coin would be heads or tails. It would include two elements, and we'll see others as time goes on. So now let's define capital E. Remember, we defined the sample space capital S, but now we talk about an event, and an event defines something that might be happening with the experiment, with the trial. So we define the event as roll an even number. Okay, and in that case, with the sample space of 1 through 6 on a fair die, the even numbers are 2, 4, 6. Okay, so now we can start talking about, now we get to the probability piece of these things, of various experiments. Okay. Now, if we have to make sure it's a fair die and not a loaded die, there are certainly ways you can create loaded dies that create unfairness in the outcomes, unfairness in the potential, events probability in the full sample space. So, what are the rules of probabilities? And this is, we'll talk about this, and we'll see a few here that are really important. Okay, so there's two key parts to the rules of probabilities. One, the probability of any event that we're talking about. In the previous case, it's rolling an even number when we throw a fair die. It's got to be between 0 and 1. It could be 0, it can be 1, but it's got to be between those numbers. Okay, it's got to be some number between 0 and 1. And the sum of all the probabilities of all the outcomes has to equal 1. So sample space we defined as, all those outcomes. You add up the probability of all those outcomes, E sub 1 to E sub n, depending on n, the number in your sample space. You add them up, that's got to equal 1. Now this should be relatively intuitive, that the probabilities have to be between 0 and 1, and they have to, when you consider the whole sample space, they have to add up to 1. So we're going to check this whenever we build a little probability model. We're going to make sure we satisfy the rules of probabilities. And we'll see this a few times in the lecture. So I just previewed this slide. The probability model lists all the possible outcomes of an experiment in probability. Okay. And they have to satisfy both of these rules. To be a probability model, it has to satisfy these two rules of probabilities, and then we can call it a probability model. So let's look at something. Here's an example. This is the probability of choosing one M&M out of all the M&Ms in a bag or a bowl or whatever you have. The probability of a color of the M&M being brown, yellow, red, blue, orange, or green is given here. And this is from the manufacturer. So they must do this on purpose. They must have this magic, way of getting these probabilities set. So let's consider the rules of probability. The rules of probabilities. Is rule number 1 met? Are all these probabilities between 0 and 1? Yes. And then do they add up to 1? That's rules of probability number 2. So let's look at number 1. Each of those is between 0 and 1. So rule number 1 is satisfied. And when we add them up, we can see they all add up to 1. When we add these 6 probabilities up, these 6 proportions up, they add up to 1. So rule number 2 is satisfied. This table 1 is a probability model because it satisfies those 2 rules of probabilities. Now, remember, probability can be 0. All right. Now, the probability being 0 means the event is impossible. And if the probability is 1, then it's a certainty. Okay. But as we know, we have to live our lives as analysts, data scientists, statisticians, just thinkers. We have to understand that certainty is not the game. It's rare we talk in certainties. Certainties is not the way to think about the world. We should be thinking about the world as probabilistic, as a probability that we think of. Okay. So, but also we have to define an unusual event. An event that's not 0, but it's close to 0. Low chance of occurring, low proportion that it's occurring. We call that an unusual event. and in statistics. These days, when we talk about unusual events, we're talking about the probability generally being under a 5% chance. This is an important part of the second half of the course because we're going to be talking in probabilities when we do inference. When we do inference, we sort of say, okay, we accept that 5% chance of, being unusual. We'll accept the unusual when we do lots of conclusions from our inferential analyses. But we'll get back to that. We'll get back to that later in the semester. So, three kinds of methods in probabilities. One is empirical. Two is classical, and that requires disjoint events. We'll define that in a second. And three is this subjective way to think about probabilities. We're going to define all three. That's really the important step here right now. Excuse me. I'm so sorry. Oh, that's gross. I hate to do that. I apologize, but I couldn't help it. So, empirical method and probability. The empirical method uses what we call the empirical approach. So it's collecting data on sort of what really happened. We observe something and we calculate the probabilities based on that. Okay. So let's say we were observing an unfair die or an unfair coin, and we wanted to understand how unfair it might be. We have the suspicion that the coin is unfair. What we would do is just flip that coin a bunch to see what the outcome was, what the proportion was. If that coin was, a 55% heads coin by just the way it was, that's what we would see with using the empirical approach. We would just do lots and lots of uh, repeated events, repeated trials in an experiment to get at the relative frequency of the event. So if we want to measure heads on a unfair coin, we would measure the relative frequencies. We've talked about relative frequencies before. Remember, frequencies are the counts, and then we made it a proportion, we made it a percentage to get to relative frequencies. So the probability of any event, that's P, capital P, bracket, parentheses, capital E, that's the relative frequency, that's the proportion of the event. And it's based on the number of trials you do in any experiment. So this is the empirical approach. And it really is about collecting the data and using that collection of data as your sort of sense of the true probability of something, of this event in this sample space. Okay. So let's again give it an example. What are the relative frequencies to approximate the probabilities to give a probability model of how something works? So this example is an insurance agent insures 182 teenage drivers. 24 of them had to file a claim. So what's the probability a teenager will file a claim? It's just the 24 over 82, 13%. So, because we collected these data ourselves, we wanted to answer the question, what is the probability that a teenager that I insure in my insurance company is going to make a claim on the auto policy? Well, we just collect the data. We empirically get at 13% because that's the data we have to get the probability. So hopefully that's clear. This is a way to get a probability, this probability here of 13%. The way to get that probability is empirical. We just collect the data ourselves. And then we can say this. We can say, so for every 100 insured teenage drivers, we expect, and clearly we don't say no, we don't say anything definitive. It's a probabilistic statement, an expectation that 13 out of 100 insured teenagers will have a claim. And that's just from empirical observation. It's not any kind of, you know, uh, known thing. It's expected based on our observations. Let's do this again. All right. This is another table. This is a collection of data about how people get to their workplace. And there's 6 different ways of getting to your workplace, categorized this way. And it was counted like in a nice categorical data set. We surveyed 200 people, put them in categories, and now we have the frequencies. And now we can hopefully build a probability model, but we have to check that it is truly a decent probability model. So, what are the steps to go from a data set like this of frequencies in a certain category to probabilities and a probability model? It should be fairly intuitive because we've talked already about relative frequencies twice already in the content for this class. We're going to see it again here. This is again about relative frequencies and proportions empirically observed, leading to a probability model about how people get to work. Okay, so that's what we're doing. So that's the whole point of this, is to build our probability model, and we're estimating the probability that here's the question. Estimate the probability that a randomly selected individual gets to work by carpool. And then we're going to interpret the result with the right language we would use around probabilities and what it would end up being. And then we'd ask another question. Would it be unusual to randomly select an individual who walks to work? Well, let's go through these. Let's go through these A, B, and C questions here in our example. First, check that it's a probability model. Okay, so we go from table 2 here to table 3. You see how it goes from frequencies, we call it probability. It's the same thing that we did before called relative frequencies. So, but we call them probabilities now because that these are equivalent terms. Relative frequency is the same as probability. You can always think that. So we can calculate the drive alone proportion. The drive alone probability is 41.5%. So that is our empirical observation about how many people are going to drive alone to work, how many carpool and public transportation, etc. So now we've gone from frequencies to relative frequencies or probabilities. And now we can ask the other 2 questions. The other question was estimate the probability that a randomly selected individual carpools to work. We should see it already. And then we'll learn how to interpret that probability. And then would it be unusual, and this is the word that we're going to use at sort of at 5% is our rule of thumb, to randomly select an individual who walks to work. Okay. And if we look at that walks to work, we can see it's 2.5% is the probability in our empirical data set, our data set that we collected. So we're going to call it unusual because it's less than 5%. I've already previewed exactly what the next 2 slides show. Part B is 11% are carpooling based on our empirical observations. And we would say it this way. If we were to survey 100 individuals, we would expect about 11 to carpool to work. Again, expect. This is sort of the way we would say things. We'd say expect. We would never use the definitive words at all. So the probability, this is part C now here, on to C. The probability that an individual walks to work is 2.5%. And because it's less than 5%, we're going to call that unusual. We're going to use this 5% rule a lot as we go forward. So hopefully that's interesting. A big way to get probability models, which are very, very important in statistics, is empirically to collect the data and use our sample as the guideline for what the probabilities will be. Okay. Now let's go to the classical method. This is different. The classical method is different than in the empirical method. Empirical method, we collected data ourselves, our own observations, and said, yeah, we kind of expect the probabilities to be around what we collected. That's our probability model. Our estimate is from our observations. Classical method's different. This is what you might have learned in previous studies of probability. This is commonly described as a method of probability. But the key to classical method studies is you have to have equally likely outcomes. That's not true of the carpool data. It's not true that walking to work and driving alone have equally likely probabilities. We cannot use the classical method for carpool getting traveling to work, but we can with things that have equally likely outcomes, like rolling a die, like flipping a coin, like pulling a card from a deck. These have and fair decks in fair coins and in fair dice, you can see hopefully that they're equally likely outcomes. So that's the key thing. When we use the classical method, it has to be equally likely outcomes. So the way we think about equally likely outcomes, remember, the probability of the event is some piece of our probability model that we want to study. The probability of the event is the number of ways that event can occur over the number of possible outcomes because it's equally likely. All the outcomes are equally likely in flipping a coin or rolling dice. We can sort of say the event might be, how do I roll an even number when I throw one die on the table? We can start using the classical method now to do that with equally likely outcomes. So we can just do a division here. This n here in this formula, the probability of the event is the number of times n that the event occurs and the number in the sample space. We talked about here's the words definition. This should make sense that if we have equally likely outcomes, this is what's going to happen. Okay, so let's give an example. Of course, a pair of dice are now rolled. They're fair, and everything's equally likely. The first question in our classical method is, are there equally likely outcomes? Yes or no? Is this equally likely? And if it is, we can rely on the classical method, and it really is a good way to proceed. So, what's the probability if I have two fair die? I have a pair of dice, and I want to throw both. What's the probability of rolling a 7? Well, what we have to get the sample space. Right, that will be the denominator. The number in the sample space will be the denominator. The number of in the event here, the probability of rolling is 7 will be in the numerator, the count. So the number of uh, ways I can roll a 7 divided by the number in the sample space will be exactly this probability, and we can use the classical method to calculate this probability. Here's another question. Question B, what's the probability of rolling snake eyes? In other words, a sum of two, one and one on each die. And what's the likelihood of rolling a 7 versus rolling a 2? In other words, what's the difference between A and B, the proportion between A and B? Here is the picture. Okay, let's look at question A. What is the probability of rolling a 7? Well, in the graphic are all the different outcomes of rolling the two dice, the pair of dice. Okay. And you can see there's 36 different ways you can roll the dice. So n of the sample space is 36, the full sample space. Now the roll of 7, there's 6 ways to roll a 7, and you could sort of just look at the red numbers here. The red pairs are all adding up to 7. So that's 6 red pairs. When I look at the full field here, you can see them on the diagonal. All these red dice here are 7s. So there's 6 outcomes. So the probability of rolling a 7 is 1 out of 6. Okay, and I could build a probability model, right? I could build a probability model of all the outcomes. And if you're a backgammon player, if anyone likes games of chance, you really have to study this because this is the key to really getting good at playing backgammon. The people who play backgammon know this probability model of rolling a pair of dice intuitively. They've done it so much they know this data set of this probability model because they need it to play the game well, to play backgammon well. So for those of you who have ever played backgammon, the people who do well are the people who already embrace this probability model as they play the game. So part B of this example was what's the probability of the event of rolling snake eyes? A 2. Well, there's only one outcome here that's 2. That's what in the upper left corner. It's 1 of 36. There's only 1 of 36 ways of rolling a 2. The third question, C, was to compare the probability of rolling a 7 and the probability of rolling a 2. And so, with these probabilities determined by the classical method, because we know we have equally likely outcomes, we expect to observe about 6 sevens and only 1 2 when we throw dice out of 36 rolls. Okay. If we roll the dice 36 times, 6 times we'll get a 7, 1 time we'll get a 2. We expect that. Okay. Again, expectations, not definitive. All right. So let's do this again. We saw this before. Remember, Sophia had 3 tickets to a concert. And this case, we only have 4 friends who wanted to go to the concert. Before we had more. But this is the case where Sophia wants to randomly choose 2 of her 4 friends that can go with her. She has 3 tickets. Of course, she's going to go, and who else goes? We can ask the question, what's the sample space? That's crucial because we need the sample space to get the count of the sample in the conditional model. That will always be in the denominator. If we think it's equally likely outcomes that it's going to be a random choice of 2, Jewel, Ashwin, Ramon, and Destiny, 2 out of those 4 people, we have to get the sample space because that'll be in the denominator of our calculation of the probabilities. What's the probability that Ashwin and Ramon, that pair, will attend the concert? That's one question. And another question would be, what's the probability that Jewel attends the concert in all the outcomes? Well, how do we get the sample space? We have to sort of consider how we put these 4 people in pairs. It can be Jewel Ashwin, Jewel Ramon, Jewel Destiny, Ashwin Ramon, Destiny Ramon. So we can just empirically list them. We can brute force the list, but we still have equally likely outcomes and use the classical method. So interpret probability of part C. That's the right way we're going to say something. So here's table 4. Table 4 is the list of outcomes that we have choosing 2 people from 4. There's all these different ways. So sample space, that was the question A. The sample space is right here. We have 4. Table 4 lists the sample space. There are 6 different ways to grab a pair of people from a list of 4. And we can answer question B now. There's only one way that both Ashwin and Ramon, this pairing right here, there's only one way that pairing will go in the full choice of 6 potential outcomes in the sample space. So we can compute the probability is 1/6 that the pair, Ramon and Ashwin, will attend the concert. Now we can ask part C. Okay, part C was, it's down here at the bottom here. Part C, compute the probability of the event Jewel attends the concert. What are all the ways in table 4 that we include Jewel? Well, it's half, 3 of them. There's 3 outcomes where Jewel is included, 3 outcomes where she's not. So the probability that Jewel attends the concert is now 50% by the classical method. And we how do we interpret part C once we do the classical method? What would the language be that we would use? We wouldn't talk about certainties that Joule would attend the concert, but we could say this. If we conducted this experiment 1,000 times, about 500 of the experiments would result in Joule attending the concert. Okay, so now let's compare our two methods. We have the classical method, the empirical method. These are two different ways to go about it. Empirical was using a data collection scheme that we're going to use as the basis of our probability model. The classical method is with equally likely outcomes. We can lay out all the outcomes and then build a probability model that way. So let's do this two ways. Okay, we're going to use both the classical method and the empirical method to answer this question. We asked 500 families that had 3 children to disclose the sexes, the gender of their 3 children. And in this survey of 500 families, 180 of the families had 2 boys and 1 girl. How would we get the empirical probability of having 2 boys and 1 girl? Right? That's with our observations. That's using the data set we have collected. But how would we do it in the classical method, assuming that boy and girl is equally likely, right? We can use the classical method if it's equally likely. So we would do this way. So first, estimate the probability having 2 boys and 1 girls with the empirical method. Then use the classical method, assuming boys and girls are equally likely. So empirical method. Remember, it's our data collection. It's 180 had 2 boys and a girl over 500 in our sample, 500 families that we grabbed. So it's 36% in our data set that we collected. So we would say this, the probability that a family of 3 children will have 2 boys and 1 girl is approximately 36%. So that's by the empirical method. That's the empirical method. This is a chart. Look at this table. What we've done here is said, okay, first child could either be a boy or a girl. Look at this section here. Our first child can either be a boy or a girl. The second child, given that the first child was a boy, would be follow this part of the tree. It could be a boy or a girl too. It's equally likely that the second child, in either case, independent of the first child, could be a boy or a girl. And then the third child could be a boy or a girl. We've just delineated all the different ways you can have sexes occur given 3 childbirths where it's equally likely you had a boy or a girl. So these purple circles represent the equally likely outcomes, and we have to have that for the classical method, the equally likely outcomes of 3 children in a row. You could be boy, boy, boy. That's one way you'd have an outcome of 3 children. But you can sort of see when you list all these different potential outcomes as you follow the tree diagram, these are all equally likely. There's 8 different outcomes in 8 different orders. But the question we had was, what's the likelihood of having 2 boys and a girl? So we have to look at all these different equally likely outcomes where there's 2 boys and a girl. Well, no, no, no. Yes, there's one, 2 boys and a girl. Nope. Yes, there's 2 boys and a girl, 2 boys and a girl. 3 ways in these 8 equally likely outcomes, 3 ways we get 2 boys and a girl. And because it's equally likely at every step, have a boy or a girl, we can use the classical method to calculate the probability model and answer the question. So sample space is here's the tree method. We just lay it out. This is the sample space. The question B was determine the sample space using classical method. And there are 8 different equally likely outcomes. So this is the sample space. Okay, the sample space is boy, boy, boy. In this case, it satisfies our event question. two boys and a girl, two boys and a girl. And the third here is there, this one, two boys and a girl. All right. So sample space, 8 different outcomes, equally likely. And so the number in the sample space is 8. For the event, two boys and a girls, the number in the event space is 3. They're equally likely. So we have the probability of two boys and a girl using the classical method is 37.5%. Now that's different than we got with our empirical data, which is just fine because we use 2 different methods. Remember, classical can only be with equally likely outcomes, and we can use it when we know that. All right. So comparing them, we can look at the probability is 37.5% of having two boys and a girl. So this is what we could say. If we repeat this experiment 1,000 times, the outcomes are equally likely. You expect 375 of the trials of 1,000 to have two boys and one girl. All right, so that is so hopefully the comparison when you go through these slides and look at the video, you'll see how the classical method, empirical method are different, but this is a really good preview for what we're going to be doing when we do inference. We're going to be using the empirical method a lot in the rest of this class to understand how to do inferential statistics. Now, remember the third technique was called subjective probabilities. So let's interpret that subjective probabilities. This is the third of the way to assign probabilities. We can assign probabilities, build a probability model, empirical and classical. We just finished that. But what's subjective? Well, subjective is this, it's just subjective. It's what people might say. So it's the basis of personal judgment. And you could put any kind of weight you want on these subjective probabilities. Okay, so I don't know how clear this is, but a lot of times we're about to start a new baseball season this year, 2025. There are a lot of experts in baseball who try to really understand the importance of a construction of the team and how it might lead to better outcomes. Which team might win the World Series? And you can say it different ways, right? So we could say that there's a 20% chance that the Dodgers are going to play in the World Series, okay, this year. Now, that can be said by anybody, right? It could be a subjective point by anybody. And another person might say, oh, it's the Yankees who have a 50% chance of playing in the World Series this year. It's all subjective. It's not based on empirical data. It's not based on the classical method using uh, equally likely outcomes. So that's the point. It's just subjective. So we covered the 3 different ways to build this probability of events. Any questions on that before I move to the 5.2, the next section? So now we're going to get into some addition rules and the complementary rules, okay? And we have to define what disjoint events are. The general rule here, we have 2 rules, the general addition rule and the addition rule. It depends on understanding mutual exclusivity or disjoint events. And then we can think about the complement too, which isn't that hard once we understand how we think about the sample space of things. Okay. So let's define all this. Okay. What is the addition rule? And we say it this way: if 2 events are disjoint, they have no outcomes in common. Okay. If 2 events, remember we talked about events before, events are part of the probability space. We talk about the probability events given the probability of the space. Another way to say this is mutual exclusivity. Mutual exclusive and disjoint are synonyms. So if you understand mutual exclusiveness, it's the same thing as disjointness. Let me give you graphical examples. So look at this Venn diagram down here. This is a sample space. And what it is basically the little experiment is we have a bag of chips and there's 10 chips in there, and they're labeled from 0 to 9. So as I put my hand in the bag of chips, I pull one out. That's sort of a little a little experiment to see how we would think about the probabilities here. But we can also talk about different events within this little experiment. We can talk about the event of choosing a number less than or equal to 2. That's this purple event space. So we have three ways of choosing a number less than or equal to 2. And we have two ways of choosing a number greater than or equal to 8. Greater than or equal to 8. Now, these two events are disjoint. They're not the same. Okay. Event F is mutually exclusive from event E. So, how do we think about probabilities in this case? Well, it's sort of intuitive, right? It's 10 different parts of the sample space. And you can see we've labeled S, the sample space. 5 of the sample space are not in the events that we care about. It's not event E or F, the other 5 numbers. But the other numbers, event E and F, are disjoint. They're mutually exclusive. So we can start talking about probability addition to understand better how we combine things. So the probability of event E, right? The probability of being in event E is 3 out of 10. Remember, equally likely outcomes, choosing one of these chips out of 10. The probability of being less than or equal to 2 is 30%. The probability of being greater than or equal to 8 is this event F. The probability of that event is 20%. All right. And we could do a new analysis. If we have disjoint events, we can now talk about the probability of E or F. This is our addition rule, right? We can add these up. Now, we can do it first just by looking. E or F, we'll just go straight in and go, okay, the probability of E or F is 0, 1, 2, 8, or 9. That's 5, 5 of 10. We can do it just by count, or we can use the addition rule. And here's the addition rule. The probability of E or F, this little formula here, when we look at probabilities of two events, we can add them up if they're disjoint. Okay, if E and F are disjoint, we just add them up. They're going to be different if they're not disjoint, which we'll cover in a second. That's the general additive rule. This is the addition rule. Okay, so addition rule for disjoint events. We just did this. If E and F are disjoint or mutually exclusive events, then P, the probability of E or F, the events E or F, equals the probability of E plus the probability of F. The addition rule for disjoint events, pretty straightforward as an example. We can extend this further to more than 2. We can think about, in general, any events we care about. If each of these events, P or F or G or whatever, if all of these events that we want to look at, if all these events, the probability we want to look at, are disjoint events, then we just add them up. That's the additive rule for disjoint events for any number of disjoint events. Okay, so let's go to this example. We have the same sample space. We have the probability of being less than or equal to 2. That's event E. The probability G of being a 5 or a 6. And the probability of event F, the probability of being greater than or equal to 8. In the sample space is those 10 chips. And now we can think about 3 events. We already did probability of E is 30%. The probability of F is 20%. But now we have the probability of G, which is also 20%. Ask yourself, are these mutually exclusive, E CGF? The answer is yes. So we could do this rule here, the probability, the additive rule of disjoint events. Pretty straightforward. Okay. Now, this is just interesting. I mean, this is an interesting thing that you might want to, it's in the book. It's really kind of cool. You would think that any number that we see in the wild, any number you would observe, would have, different random beginning numbers. Okay, so we'll say it this way. Uh, you would think the first significant digit in any number anywhere would be, it certainly could be any significant digit could be any of these nine numbers. It can't be zero because we don't put zero at the start of a number, right? That's just we don't use we use 12 instead of 0, 1, 2. So it could be 1 through 9. And you would think that the first digit, the first significant digit here would be equally likely from 1 to 9. But it's not true. It's bananas, right? So this is called Bedford's Law. 1881, Newcomb discovered it, but Bedford wrote it up pretty well and talked a lot about it. And here's the key thing. The first digit probability, okay, this is the probability known as Bedford's Law. Probabilities of occurrence of each of the first digits of any number you see is this one. So the probability of any number having a 1 at the front is 30%, 2 at the front, 17.6%. The probability of any number you see anywhere having a 9 in front is 5%. Now, if you think of numerics, this might make sense to you. If not, it's okay if this isn't intuitive to you. It's still an interesting observation. So the textbook does this, and I just wanted to show you this. This is pretty interesting. And again, these are disjoint events. The probability of having 1, 2, 3, all the way up to 9 at the first significant digit of a number, these are disjoint events. And first thing we do, remember what we do with a probability model, and this is a probability model, is we check it. What are the rules for the probability model? Well, all probabilities have to be between 0 and 1 inclusive, and they have to add up to 1, all the different sub events in this probability model. Well, we can do that. So we do that. We look at it first. Is it a probability model? Yep. Each of those 9 probabilities is between 0 and 1. Check for the first one. And when we add them up, which we couldn't do in our head, but we add them up in a calculator, and yep, they all add up to 1. So this is a true model. This is a true probability model, which is really just interesting. And of course, it's been written up many times. Hill wrote an article, a very fun article to read in American Scientist, a very readable journal for anybody in this class. Is for anybody, this is for anyone to read and understand this journal. So the article by Hill was the first digit phenomenon. If I get the chance, I'm going to write myself a note. I'll upload this article to our shared drive so you can see the article if you like. It's just a cool, interesting thing. So here's Bedford's Law. We can ask questions like this. What's the probability that a randomly selected number has a first digit of 1 or 2? Well, it's the sum of 30% and 17.6%. So that's what it is. 47.7% that all random numbers we find start with a 1 or 2. So we would say this. If you looked at 100 numbers anywhere, anytime, anyhow, we would expect 48 to begin with a 1 or a 2. Expectation is part of the language we would use here. What about the probability that it's 6, 7, 8, or 9, that the first digit is at least 6? Well, we add that up and it's 22%. It's it's 2x more likely that we have any number starting with 1 or 2 than the number starting with 6 through 9. Very interesting stuff. Okay. So now let's take a deck of cards. This is another way to think about the additive rule. So a deck of cards, 52, four suits, ranking from ace all the way up to king. Most people are familiar with this sort of structure, 52 different cards, all unique. And we can start asking, what's the probability of the event E drawing a king? Each of these outcomes is equally likely when I draw one card from 52. Again, having it equally likely allows us to use the classical model to better understand probabilities. So what's the probability of drawing a king? Go back to the full sample space. There are four kings. You can see them on the right out of the 52 cards. So that's the method. The probability of drawing a king is 4 out of 52. Sample space is 52. The standard deck has four kings. Therefore, there's a 1 in 13 chance, 1 in 13 probability that we draw a king when we draw one card from the deck. 1 out of 13. Okay, so now we can do other probabilities too. We can do the probability of drawing a king or drawing a queen or drawing a jack. These are disjoint events. Okay, first we have to see the mutual exclusivity. When we see the deck of cards, there are four kings, queens, four jacks. E, F, and G are mutually exclusive. They're disjoint, so we can just use the addition rule. And again, we can use the addition rule. This is the addition rule. The probability of kings, queens, or jacks, just add up the probability of each, and we get three 13ths as our probability of getting a king, a queen, or a jack by the disjoint rule, by the additive rule that's disjoint. Now that's the addition rule, right? So the addition rule is straightforward with disjoint events, but sometimes events aren't disjoint. Let's go back to the deck of cards to talk about the general addition rule. And these are the kind of problems you might see as a student. You might have to figure out which is which, general addition rule or the addition rule. Let's look at this Venn diagram. Same sample space, okay? We have 10 chips in a bag. They all are labeled from 0 to 9. And we can talk about different events that we care about. Let's say we had one event which was odd numbers, and that would be 1, 3, 5, 7, 9. That's the event I want. What's the probability of pulling an odd number out of my bag, out of my sample space? I can also have another event. What's the probability of choosing less than 5? And that would be 1, 3, but also 0, 2, and 4. 1 and 3 are shared. This is the overlapping region by a Venn diagram. Two different events, event E and event F. And the shaded regions, this big circle is E, and the big circle here is F. So and we can say what's the event of either choosing an odd number or a number less than 5, and that would be E or F. Event E or F is choosing an odd number or choosing a number less than 5. So that's everything. But we can't use the straight addition rule. And you probably see why. So what is the probability of event E or F? We could do it by straight count. Let's do that first. How many? Well, we get 8 different ways to get E or F. Only 2 different ways we don't get the E or F, which is odd and less than 5, or I'm sorry, or less than 5. It's only 2 ways to do that. Okay, so we can do by direct counting. And this is just counting 8 of 10. We can do it straight counts. 8 of 10 or 4/5 probability, 80% probability we get an odd number pulled or a number less than 5 pulled. But let's do this. This is our addition rule. Remember the addition rule? P of an event E or F is the sum. Well, if we did the straight sum of probability of E, which is 50% odd numbers, and we did probability of event F, which is less than 5, that's also 50%. That adds up to 1. That's not the case. We had 80% as our outcome. So this general addition rule does it this way. The probability of E or F is the probability of E and the probability of F minus the probability of E and F. Now, we call this general because if we go back to the disjoint events, what is the probability of E and F? By definition, the probability of E and F in disjoint events is 0. That's the definition. Means there's no combination that's the same. So here is how we get to the fix to get to 80%. We have to subtract the probability of E and F. We have to subtract, this shaded region, which is the overlapping region of E and F. That's this right here. This formula right here is the general additive rule, okay? The general addition rule. So for any two events, and this works for disjoint events too. This works also for non-disjoint events. It's the general rule. So P, or the probability of event E or F, is the sum of each of those probabilities minus the overlapping probability. So that's the general addition rule. So let's go through an example. Let's understand better the general addition rule. Here again is the description of a general addition rule. In this case, we're taking a standard 52 card deck, and we're going to compute the probability of event E, drawing a king. We already did that. Probability of event E is 1 out of 13. And the probability of drawing a diamond. Drawing a diamond, there are 4 different suits. So probability of drawing a diamond may be intuitive to most folks here. It's going to be 1 out of 4, 1 out of 4 chance of drawing a diamond. But there's one card that's the king of diamonds. There's one card that is both a king in event E and a diamond in event F. So we have to subtract the probability of the king of diamonds in the general addition. All right, so here we go. This is what I just said. The probability of a king or the probability of a diamond is the probability of the king, the probability of the diamond minus the king of diamonds, because that's in both. That's in both of the events, just like we did before. So we have 4 out of 52 kings. That's the probability of a king. 13 out of 52 diamonds, and 1 out of 52 king of diamonds. So we do this math. We get 16 outcomes out of 52 will be 16 out of 52, or 4 out of 13 are the ways we would get the probability of a king or the probability of a diamond. Again, hopefully this is clear by the general addition rule. Now, let's go to a contingency table. Okay, a contingency table we finished up yesterday, last lecture. Again, this is categorical data. These are people over 15 years old in the United States. They're categorized as either male or female, and by their marital status: separated, divorced, widowed, married, never married. And you can see this is the contingency table. We call that a two-way table also from last time. And pretty straightforward description. Again, categorical data. And now we can start thinking about using the general addition rule to start understanding a probability model. Where does a probability model come from? Well, it's a lot of relative frequencies, okay, proportions based on the question you ask. So let's go through different questions. All right. Here on this table below, table 6, what's the probability that a randomly selected U.S. resident, 15 years old or older, is male? Well, you might have a sense of already how to do that, but that's a question. We might want to consider, what's the probability a random selectedly person over 15 is male? What's the probability that a randomly selected person is widowed? And you might have a sense of how to do that with relative frequencies, right? You think about how we set up the contingency table, the marginal distributions, the marginal relative frequencies. We started doing conditional questions as well last lecture. All right. What's the probability that this is where we get to the addition rule? Uh, what's the probability that a U.S. resident is widowed or divorced? Widowed or divorced. This is our addition rule again. And what's the probability that a randomly selected U.S. resident is male or widowed? All right. So we're going to go through these 4 different questions based on this contingency table, this two-way table, and just answer these questions. What's the probability? All right. So let's look at it. First, we have to get to all these marginal frequencies, marginal relative frequencies. We did this last time. So we'd start adding up all the rows, and then we'd get a sense of the marginal look at marital status for both males and females. And then we'd add the margins for the sexes based on also separated out in by sex, but also get the breakdown, the sum there for all the different marital statuses. And that's what this says. We're adding things up. Turns out in this population, there's 272 million or so residents 15 years or older. So we're going to ask different questions now about this. First, remember the first question? A, determine the probability that a randomly selected U.S. resident is male. How do we do that? Well, we got to add up the male column, get a number and a frequency and a relative frequency. Female column, relative frequency, or versus the total. Remember, we know the total. We know these various ways. So how do we do A? And we're also going to do B. The question is older or widowed. Now we're doing the additive rule when we do probabilities of older or widowed. How do we do that? Well, add up all the males. Turns out this column here of numbers is 133.6 million. And the full set of numbers, the full total here of males, females, is 271. Okay, so what would we do? How would we get that answer, the probability of male in a random set? Well, the probability is 49%. It turns out it's not 50-50 when we look at the 272 million people over 15 years old. 49% are male. Okay. A lot of reasons why it's not 50-50, but it's not 50-50. Okay. Just know it's 49%. And then we could get at the question, older or widowed. So we have to now add up the marginal relative frequencies that we get from the column to the right, which is the sum of the rows, right? As we get those. So what we have there, older is a widower. I'm sorry, we don't add these up yet. We can just add these two numbers here. 3.5 million, 11.5 million is 15 million. The full population is 271.7. So 5.5% of the population is widowed. We do it that way. But now let's do this question. I'm sorry. What if we ask the question in part C, widowed or divorced? And now we get to the addition rule that we've been using. We have to see that these are disjoint events, so we can use a straight simple addition rule, which means widowed or divorced, which is our question, is widowed plus divorce. And that'll be over here. We'll add those up. So widowed is 15 million. Divorced is 28.9 million. We see that this is the addition of these two numbers. 12.3 plus 16.6, 28.9. We add those up and we get 16% of the population is widowed or divorced. Widowed or divorced. And that's how we use our contingency table to get that. Finally, we're going to use the general addition. What's the probability that a randomly selected person is male or widowed? Male or widowed? Well, we have to calculate the probability of being male. We did that before. Widowed, we did that before. But there's there are a group of people who are male and widowed. There are 3.5 million people who are male and widowed. Okay, so we have to do the general addition rule to get the right probability there. These are the probabilities. We did these previously. This is the male probability, this is the widowed probability, and this is the male and widowed probability. We do that, and 53.4% of Americans over 15 years old uh, is male or widowed. Okay, so that's how we do this general addition. All right. Finally, the complement. Let's go through the complement rule. A complement of an event is just the other part of any of the event. The not event part is the complement event. The Venn diagram should help you here. Okay, so the probability of the complement of the event is just one minus the probability of the event. Probability of the event is just the complement is all the rest. And we know the full total of a probability model is one. So the probability of the event, complement of the event should be the complement. This is the picture, and we'll pick this up. We'll pick this up next week. But the probability of the complement is everything that's not the event. Here's the probability of the event. Okay. Here's the probability of the complement of the event. Okay. It's the region outside the circle, which represents the probability of the event. So 52, this is data, this is the example, probability complements. 52% of Americans play the state lottery. What's the probability that a randomly selected American has not played the state lottery? Should be pretty straightforward just by the language, what we should be doing here. Not played the state lottery is one minus played the state lottery. It's the complement, so it's 48%. This is the complement probability. Pretty straightforward. So we would say this is how we would interpret our from our data set. The probability of randomly selecting an American who has not played a state lottery is 48%. All right, let's do this. This is another categorical data set. These are people, the income distribution in 2021 of Americans. We have annual income less than 15,000 is the lowest income category. The highest income category is $200,000 and over. Okay, and you can see the distribution of the people in all these different categories. So again, categorical data set. We take people, we put them in a category based on, the answer to the question, what is your income in the United States that year? Okay, so let's compute the probability that a randomly selected household earned the following income. What's the probability of earning $200,000 or more? This is pretty straightforward. Okay, we already have the data set. The probability of earning $200,000 or more is the probability of selecting a household, and that's 11.6. This is 15,219. And let me go back to the full data set. Here it is. This is the full data set. Okay, and there's 15,219. To get that relative frequency, we had to get the total, and we added that up. The total is there are 131 million households. The probability of a household being over $200,000 is 11.6%. So 11.6% of the country households earn more than 200,000. So let's compute complements. Now we can ask questions on the complement. What is the probability of doing less than 200,000? What's the probability of the household being in a household that's less than 200,000? Well, it's the complement. We already calculated this one right here. The probability of $200,000 or more is 11.6%. The probability of a complement of the opposite is just one minus that. So it's 88% is less than 200,000. And you should read this last sentence here. If we randomly selected 1,000 households in 2021, we would expect, again, we use the language expect 884 of them have household incomes less than 200,000. Okay, so again, same data table. Here's another example. What's the probability of getting at least 15,000? That's our question. So now we're doing at least, and now we have to think about complements. So we know the probability of less than 15,000. This is from our table. We can see it right here. 12,202,000 earn less than 15,000. So those that are at least 15,000 is the complement. 90.7% of the households we expect to be over $15,000 annual income. Okay. I actually got through them, so I went a little long. Hopefully, it's a recording. We'll be okay with that. Any questions before I wrap up this recording? Well, thank you for joining me on Zoom. I apologize for my respiratory distress and my infection. I'm glad we could do it this way. That's the power of Zoom. But we'll be back next week. So this recording will be uploaded to the shared drive. Everybody can see it, review it. For the homework this weekend, the homework will be, I'll finish that tonight and upload it for Sunday. So everyone has the homework for Sunday.